Modeling inversion in Escript. So I will say a few words Escript for people who haven't heard about it yet. I will talk about 2D modeling. I will give you one example of an example I've done. You have done a few years back, but I've been contacted the last couple of weeks about this problem, and therefore I pulled out all the old slides and thought I'd show it to someone, and maybe it stimulates my thinking a little bit. And then I will talk about 3D inversion as well, which is my favorite topic at the moment. Okay. So, okay, Escript. So this is an old project actually running for 13 years now. And the origin, so we started this out of the XS MNIF, and it's now carried over to the Auscop NCRES project. So the original idea was that you have mathematical models that can thinking back in 2003, there was not a lot of software around doing modeling in geosciences. So what we want to have is a very flexible tool. You can build models very quickly, and we used some sort of a PDE, partial differential equation-driven model, and you have some geometry here, like this would be a data set for an EIT inversion. And you want to put this together to some form of script, no? And then you want to run it on your desktop and maybe on a parallel computer, like in POSI. No? And the idea is, the whole idea originally was that this script is abstracting you from these kind of problems. What do you do when you parallelize your code? Efficiency, scalability, these kind of things. And we want to have some sort of easy way to describe these kind of models. This was a driver back 15 years ago, 13 years ago when this is, and well, it's still there. And it's all written in Python, which was at that time quite unusual. These days everybody does Python, but back in 2003, actually not everybody was happy with this. And I had a lot of discussion with people, why not in MATLAB, and blah, blah, blah. It was not so clear at that time that Python will actually fly. For me, it was clear it will, that's why we use Python, but anyway. So I think the next slide is giving you a little more detail. So it's running for 13 years now, and we have got about, it's probably a conservative assumption, $33 million to support that development, and we'll hopefully get that funded end of next year with new NCRES money. And again, so it's modeling with partial differential equations, and as it's very important, it's some sort of design. It's designed for doing rapid prototyping. It's not there to have an optimized code for a particular application. It's having a code an environment which allows you to develop quickly new models. Right? So it's not always the most efficient way of doing things. So this often, particularly in the inversion arena, I've got a lot of discussion with people saying, oh, how fast is your code? But you could speed up some of the inversions in particular by probably an order of magnitudes easily if you would have a better implementation. But as I said, the motivation is really having fast development environment. And it's easy to use, and so you don't have to be a software engineer. This is one of the important things. That we didn't want to have a whole group of people developing a simple inversion code. You want to do this yourself, playing around with parameters, things like that. And there's supercomputing for masses. So once you have tested this, it's all running, and Alan is some sort of prototype of that user, and then you go up and scale it up to thousands of cores. Right? And as I said, it's all in Python, which is a language much easier to use than C++. If you've ever done C++ programming, you probably will understand what I'm talking about. Okay, so it's using finite element methods to do this. The idea is you're using, have to write this PDE in a variational form. There's things you don't really see in the script. I'll show you in the script in a minute so you get an idea how that works. So the finite element means use continuous piecewise linear, or you could use higher order approximation if you want. That results then in a sparse matrix, which you need to solve. And then you parallelize this by domain decomposition. This is some sort of what happens in the background of Escript, but when you write a script, you don't really see these kind of things. That's all hidden by the user. No? Particularly if this here can be a very annoying exercise if you try to do this, splitting the domain into pieces, distributing it, collecting the data, all these kind of things. Again, so I'll give you a little bit of an example. So basically what you need to do if you have a problem, you have to map it to this kind of second-order differential equation. So we have to basically say in your script what is A, what is B, what is C, what is D, what is X, and what is Y. And the really tricky bit, the really trick is you can have several of these, and you can hand over solutions from one differential equation, put it as an input in, as like a coefficient of another differential equations, and this solution can be input of another differential equation, and so forth and so forth. And that's all some sort of hidden from the user what is required to some sort of mapping, connecting these differential equations. That's the whole trick. So I can give you a quick example. So this is a baby example. It's like solving temperature fusion problem. So this is my idea of the world here, of the Earth. Simplified model. So that surface, we put temperature at the top. We have a little temperature source here. Tc, I know we have some permeability. Rho Cp is a heat, what's it called? Heat transfer? No, heat production rate, or what it's called. So what you need to do, you discretize this in time. Like if you're really lazy, you do something like a backward Euler scheme. So you're approximating time derivative by this term here. You plug this into the equation and then put everything when time n on the left and everything from the last time sub tn minus 1 on the right. And you end up, sorry for this. So you end up with an equation where you can identify A and you can identify D and you can identify Y. Basically what you need to write a script, a Python script, which basically say this is A, this is D, this is Y, get the solution. That's part of the idea. And then you have to have a process that progress that in time. In an inversion code, you would some sort of update the physical properties. Okay, this is some sort of an example of how you would implement that. The important bit is here. You would read in a domain, create a domain. If that's run with your desktop, this is an easy exercise. If you run this on a parallel computer, then this would be actually distributed across thousands of cores potentially. And then we define the linear PDE, and then we say what all these coefficients are. We set an initial value, and this is the loop which does the time integration step, moving it forward in time. So we update the right-hand side here, get the solution, we write this out for further investigations, and then you iterate this in time. So this is the whole script, and you can run this on your desktop or potentially on a mobile phone if you have Linux installed, or on the POSI Center with no changes to the code. This is some sort of the whole trick in the whole exercise. And it, yeah. And so important, as I highlighted, as I said before, and I just highlight this again, there's nothing in this script which talks about parallelization. And that's an important bit in the exercise. So you can jump over this. So this is a list of applications we have done over the years, a long list. So one is this is what we did a lot on convection modeling here. This is Thomas knows this one about convection in aquifers. This is a paper Thomas and I wrote many years ago. That's on erosion in porous media. So this is actually a very difficult problem when using a level set method to model the surface interface. You can see there's a fractional structure in this interface between the different phases. Okay, I want to give you one example, which I have, as I said, people talked. Actually, last week, someone was asking me, and I got a phone call a couple of weeks ago about this problem: is seismo-electric effects. And this is a project I've done with Simon Shaw, also a couple of years ago. Unfortunately, Simon decided not to finish his master thesis, but it was actually a very interesting project, I thought. He didn't like that. So at the end, so this is a scenario. I'm not is everyone familiar with seismo-electric model? You're familiar with these things? What that is? No? Okay, this is an interesting effect which you can measure in the field. Actually, so this is my model geometry. Think of this as here being a wet layer, right? Like an aquifer or coal seam, things like this. And what you can do, you can create a seismic event, in easy case with a hammer. The wave propagation will propagate through the material, and that will induce a current flow in that layer, which you can measure on the surface. Okay, this is called a seismo-electric effect or kinematic, electro-kinetic coupling. It's a very small signal, but you can measure it. So this is some sort of how that works. So if you look at the pore surface here, what happens there is a charge layer is forming on the surface of the pore, and that separates the ions in the fluid. So if you think about putting a wave through this creates a current, right? You stimulate a current in there. And it creates an electric field, and you can measure this on the surface. So this is the equations you need to solve. So it's a wave propagation equation, and there's a Darcy law for modeling the fluid flow. You can make a more complicated model with actually simulating the propagation of the wave in the fluid, but because the friction is so high, you don't really see this. So this very simplified sonic model, which is propagation of pressure only in the solid, is sufficient in this model. And then you have also the simple electric potential equation to solve here. So sigma is conductivity, U is the electric potential, J is the current being induced by the wave. Okay? And then you can calculate electric field, and you can measure this on the surface by putting electrodes in the ground and taking your basically voltmeter between them, and you will see effect. So the interesting one is this coefficient QV here, which links the fluid flux with the induced current. This coefficient QV here, which is what called basically the coefficient of electrokinetic coupling. And it's interesting to see that this is actually correlated to, it's not a very good picture, but this is permeability and this is QV. And you can see there's a very strong correlation between these two, right? So basically what that means, you could theoretically use that technique to recover permeability. No? Because if you would do some inversion getting out QV, that would give you an approximation or on a proxy for the permeability. Okay, now this is a bit of movie we did. Now this is Thomas, you will like that, because it's a spectral element, finite element coupling. So this is a layer here, which has a high conductivity and high permeability. The wave is created up here. You see the wave traveling through. I run this again, I hope I can do that. No, I can't. Can you do this? No, come on. Sorry. Now maybe go back. I think now it died. Give it a minute. So you see this is the layer with a very high electric conductivity, and I hope as this comes up again, you will see that an electric dipole is created when the wave is entering that interface, right? This electric dipole is creating an electric field which you can measure. So you can actually detect by looking at the travel time, the time delay between when the electric signal arrives on the surface relative to the start of the seismic event. You can work out what the depth is. No? If you have that. I'm a bit worried because it looks like this thing has died. No, doesn't do anything. Okay. Okay, I'll control it a bit. Uh-oh. Can't even go out there. Control delete. No. I think I have to restart it. I'm sorry. I can't even restart it. Sorry. Okay, here we go again. Yeah. So we have implemented this in Escript. So there's a spectral element solver in Escript for the wave propagation part, and then there is a coupling with the finite element method to predict the electric potential, which is solved in each time step, basically. Not in each time step we solve it. Okay, I hope that works now. No. Close your eyes in case. Okay, here you go. Oh, we don't need this. Get rid of all this. Okay, there we go. So let's just get to the right slide. I'm going to jump over the movie and I want to show this again. Start with this one. Okay, so this is the result from the numerical simulation. So this is offset from the source, and that's travel time, and this is the electric field amplitude, of, in this case, a horizontal one. And you can see there's this function of, you look at the offset, there is a peak here of the signal, and that's actually half of the depth of the interface. You can prove that. So if you can detect this, you can basically work out depth and also strength. So if you do an AVO analysis, that would help you to understand that quite well, what that all means. Okay, so this is some sort of we could run this in 3D as well, but I have to say I haven't done that because it's quite a time-consuming exercise. Okay, now I will talk a little bit. How we do time-wise? Half an hour? Yeah, that's pretty good, no? So I'll talk about bit-odd inversion. And so inversion, in a way, I use that term, and there's a lot of people talking statistics. They some sort of have a little bit of a different interpretation what they understand of inversion. So for me, this is always a very deterministic process. So we have observations on the surface, on either surface, and then you use some physical model to predict some properties in the subsurface. Typical example would be gravity anomaly, and you want to detect changes to the density. The process normally works that you have an initial guess. So this is for an ERT analysis. So if you have an initial guess for the conductivity, you make a prediction of the conductivity based on injections you do. You calculate the difference between your prediction and your observations. If that's small, you're happy. If not, you need to update your conductivity and you start again, make a prediction, blah, 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 blah. And you can, of course, the expensive part is the calculating the responses here, which you have to do basically for each experiment you're doing. And then the update process is that where you spend your time. And so mathematically, you solve a minimization problem where you basically minimize the misfit and also regularization, because otherwise the problem doesn't have a unique answer. And the whole trick in the exercise is always like, what's your smoothing factor in this? So this would be an example for a gravity inversion case where we have a regularization. We take the gradient of the density. That would be a misfit here. So this would be your prediction of your gravity acceleration, and that would be your model here for predicting the gravity potential. So in altogether, this is some sort of an PDE, as we would call it, PDE constraint optimization problem. So the trick is, you're all probably familiar with this. If you have more regularization, you get a smoother answer, right? If your mu becomes smaller, you get a noisier answer. The truth is here, some sort of personal taste in this kind of exercise. Typically, the computational costs actually go up that way. So if you have a smaller regularization, that's more expensive to do. We need more iteration steps rather than these very smooth ones. That's another aspect to think about. I don't know, I'm very in demand. I don't look about this one. The trick in this whole exercise, so it's a conventional day of doing this. And the conventional day is basically shifting the whole problem to a quadratic programming problem. So leaving the world of differential equations and basically move into the world of linear algebra, and if you want to call it in that way, you could say about economics, because that's what these people are doing all the time and doing very well. Now, what I've done in the past is some sort of moving away from this and thinking about the problem more in the differential equation context, because that's what I like to do. So if you do this, you can actually boil down this whole problem in basically 3 differential equation calls. And that's some sort of an interesting thing, because we have to solve differential equations to do the forward problem, so making a prediction of the gravity field or the electric field. Then we have to solve the gradient of the cost function, which is to be 0, no? Because we're minimizing an optimization, we're minimizing a cost function. That's as you do a lot of math. It turns out that it also involves a differential equation to be solved, the so-called adjoint problem. And then we also have to do some form of preconditioning, which is actually a very important step if it comes to very large problems. And that's basically you need to inverse the Hessian. There's a second derivative, and that's very expensive to get in practice. So we do approximations on these kind of things to accelerate the process. And again, so this is some sort of 3 PDEs you have to solve, and that's Escript world, right? This is some sort of where Escript comes into play, all right? So this is a, yeah, I was saying this is ideal for Escript to deal with. Yeah, maybe jump over this a little bit. Okay, so this is I just briefly go through. Most of people probably know about this, but that's a project Alan and I did 2 years back, 3 years back, something like this, no? 3 years probably, with also with Gian Altina, which now unfortunately has left and is now with the Hewlett and Packard enterprise company, which I'm not so happy about. But yeah. Anyway, just a minute to think about him and then continue. So I have to admit, I still try to recover from that he has left. So I have to say that Alan's probably fair to say that a lot of these things of that project was really, we need to give Gian a lot of credit for doing a lot of work in this. So this was a project where we inverted a gravity anomaly map for the Australian continent in one go. Right? Not patches, but the whole thing it's about 200 million, from memory, about 200 million cells to be inverted. And that's something we did on the Magnus on 22,000 core from memory. I think that's the biggest one we run. I think it's not the production is not what you did, but I think Xian ran one. We did one simulation with 22,000 cores. We didn't get the data out, eh? So, but it came to an answer. We couldn't get the answer out. That's the problem, yeah. Anyway, so the thing is, what we did here, we run this in a mixed mode. So we run, because if you're familiar with the architecture, so we have the processes or the nodes of the POSI, which are about 3,000 or so in memory. Yeah, and each of them has 2 processes. Each processor has 15 cores or some 16 cores. And the ones sitting in one node or one processor, they can share the memory. And that's actually what we make use of. We actually use threading to run on the nodes and then MPI to run across the nodes. So it's a hybrid mode. So we made use of the full capabilities of the machine. And probably, let's jump over this. So one of the interesting issues in this, and that's why why I bring this up, is this problem of scalability. So when you look at conventional and inversion codes, they're normally, because they're using mapping the whole problem into a quadratic programming problem, you're dealing with dense matrices, right? And that's a problem because the matrices are dense. They take a lot of memory. So you might be able to store a 200 million unknown matrix, dense matrix, even on the POSI machine. That would be a challenge. And the second problem is the complexity of the computational complexity we have to deal with and whether they are parallelized. Okay, so and some sort of what this concept of scalability basically means, if you double the problem size, you double the number of processors, you want to solve that in the same time. No? Because you have double problem size, you have double of the computer resources, the expectation that that's a win situation for you and you don't have to wait longer for your answer. Now, this is some sort of the idea of scalability, and for me, one of the key problems in inversion, because a lot of people don't pay attention to this factor. So it's not a problem if you have a little 10 by 10 grid, it's not a problem, but if you go to some sort of cases I talked about here with 200 million cells, that's a different story. Okay, I'll just jump over this, because Mark wants to say a few words as well, so I'll jump over this a little bit. Yeah. So this is some sort of, summarize this a little bit. So if you look at the number of iterations you need, this in theory, the count for this, and I talk about the iterations in the inversion process, is roughly the third root of the number of cells. Yeah. So if you have the resolution, the number of iterations will double, because you're having 2 in x, 2 in y, 2 in z direction, so it gives you a factor 8 in number of cells more, and the third root of that gives you 2. So every time you halve your resolution, you get a factor 2 of more compute time. Okay. The other thing is a lot of inversion codes have a problem. If you have more observations, the codes become more expensive to run. So basically, for each observation you add, you have one, or if you double your observations, you double your compute time. And the methods I talked about, or some sort of not really talked about, or some we use, that actually is not the case. So we're actually independent of the observation. So in ERT, this is a particular problem. Not so much for the gravity, but for ERT, a big problem, or for electromagnetic, magnetotelluric, big problem, more observations. So like look at the Auslamp project, right? This is a limiting factor that your complexity grows dramatically when you have more observations. So with this method, actually, you would get around that problem. A lot of people using Green's function, which creates dense matrices. That's like look at the conventional gravity code from UBC. They have enormous problems with this. So because even their forward problem is dense. Right. So that's one problem using directly finite element methods avoids. And that's basically these sort of ingredients, what I'm listing here, is the reason why we were able to run this simulations or inversions on large number of processes. Yeah, so this is just to highlight this a little bit, this is a benchmark we did on the NCI computer in Canberra. This is some sort of a very simple test case, and I'm coming to joint inversion now, because this is a case where we get gravity and magnetic joint inversion, but we assumed here that there is a functional relationship between connectivity, between density and susceptibility. So we're solving here 2 forward problems, 2 inversion problems at the same time. And this is some sort of a typical graph. So this is the regularization rating. That's a number of differential equations you need to solve. And you can see that if your mu goes, you can see that up to here, this is pretty much independent. The number of PDE evaluations is pretty much independent of your problem size. These are different problem sizes here. Change a little bit when you go into lower mu's, and you get a bit of variation here. But at least in this case, this is some sort of scalability, right? Because the costs for the PDEs, if you assume the PDE solving is scalable, then the inversion is actually not changing. The cost for the inversion is not changing with the problem size. Well, this is something you want, and this is a joint inversion problem. Yeah, jump over this. We pushed this a little bit further recently. And I don't have parallel benchmarks for this, but I just want to highlight this is from ERT, or electro-resistivity tomography, and we're using multigrid in this context. So what we're doing now, instead of fixing the cell size, we're starting with the coarse mesh and building up and down and up and down and down, up and down, between the coarse and the fine mesh. And well, this is an example with, this is a number of nodes, so we're starting here with 140,000, and that goes up to 10 million cells, right? And so the problem size goes from 1 to 75 here. And you look at the time here, right? This goes from 1 to 71, right? So the situation we have now is that we basically can, if we would parallelize that, we could solve that problem in constant time, putting these 2 things together. I haven't done that yet, but in theory, on the paper, that would work, you know? And we have a parallel version of this, but as I said, we haven't put it together yet. Okay. So, and you can also see the enormous speed ups. So we actually put this up from between the classical, that's what we used in Allen's code, to using AMG. And this is actually a much harder problem to solve from numerically. You can get up, getting here speed ups of factor of 20. So this is 1 order of magnitude. So instead of 10 hours, you're waiting 1 hour for your answer. On a single, this is actually on 4 cores. It's a desktop environment. No? From 10 hours, what did I say, from 20 hours to 1 hour in response time. I should finish now, no? Okay. One last thing is, I just want to say a few words about joint inversion. Promised that to Mark, so very quickly on this one. So this is recent work we did on joint inversion of gravity and magnetic anomaly data. Okay, so this is on a structural joint inversion, so we're assuming we don't have a non-relationship between conductivity, susceptibility and density. So it's just purely on structure of the rocks, if you want to call that way. So what you do in this, so this is some sort of the same cost function here. This is for magnetics, the same line we had before, but then you have a cross-correlation term in here. Yeah? So we're measuring the basically how think about this as being conductivity and this being density, how these things are related to each other. So we measure this somehow. Yeah? And then we minimize it by, so meaning that we minimize also the correlation between these two, or maximize the correlation between them, just replace that by a minus sign. Okay, so this is some sort of the idea of this. And so this is some sort of standard. There's a lot of people using this, but there's a bit of a problem with this if you do this. I hope the next, just all this. So if you do these things, this is a synthetic example we looked at, and this is some sort of result you get. Okay. So this is a 3D inversion for about 30 million unknowns which are run on, I think, 200 cores on a cluster. So this is a vertical cut through. This would give you density. This would give you conductivity, or actually the log of the log of susceptibility. And this is no correlation whatsoever. And that's where we sometimes use conventional correlation. So this is something you can see is 10 to the power of 8 is the correlation factor, so the weighting factor for this correlation. So we have to push that quite high up to actually see some form of correlation between these two. And I've printed the correlation up here. So black here is 0. That means there's no correlation. White is the contours of susceptibility and density are correlated well in that location. You can see it's all black here. That means there's presently no correlation whatsoever. Now, what you normally use for these kind of things is this cost gradient term here, this one here. So you basically take the gradient of M1, also density, susceptibility. You take the cross product of this and you square this, right? And if you do the math of this a little bit, you will see that this is 0 if these two are aligned. Gradient M1 and the contours M4, M1 and M2 are aligned, or the gradient is in collinear. And it's very large. I don't want to talk about how big, but if they are basically pointing in orthogonal direction. Now, what you can do, you can change this actually a little bit by adding an additional weighting into this. Okay? So we're using here in this case, we're using the inverse of, okay, let's say that. The reason why that actually is a problem is because this cross-correlation term is actually in the order of the regularization term, the square of the regularization term. That means if the regularization goes down, the cross-gradient term gets actually down even further. So if you halve the regularization, the cross-gradient term goes down by a factor 4. And then eventually, if you go to the minimum, this thing basically cancels out. It's not relevant in the cost function. And that's why it basically disappears, and the correlation is not very strong. So you can some sort of counteract this a little bit by adding this factor here, which there's various variations you can try this. This is the best one from my point of view. And if you do this, you can see now we get a much nicer correlation here with this one. And the other very nice thing is you see this, you can actually, and I've done a lot of tests on this, you can actually use here a standard way for this correlation rating factor. You just need 100 times the correlation for the regularization. The rating factor for regularization. This works all the time. So you don't have to play around with this, and you see that much. And you can see that, so this looks good on. If you look at it here, visually, you can also see this is again the correlation. Remember, black, not correlated, white, well correlated. And you can see all these black areas are gone, right? So we have a few spots here which are correlating to this area here, where we don't get so much good correlation, but you can see that in this, all over the domain, it's actually very good. And again, this is, did I say that about 30 million inversion on about 200 cores? Yeah, so this is a real data set from Queensland. We tried this in the same way. So again, oh, this is the one I did. Sorry, this is the one I did on 200 course. And so you can see that there's a, if you would run them in a conventional way, there would be no correlation between these, really, just a little bit maybe, I think, from memory in this area here. But you see quite nice correlations for this field data as well. Yeah, and I think, in summary, so apparently ERT is a big topic, I have to say that, for us at the moment. We're also looking at the moment of coupling simulations of fluid flow with geophysical signal prediction, and then basically reversing the process and try to monitor the fluid injections with geophysical methods. It's a project we're doing with the University of Melbourne and with University of Savoy Mont Blanc. EM and MT is another one we're looking at the moment. These are in 2D, easy to do. In 3D, it's a big challenge to do this because the numerics is very, very difficult. And we're sort of looking at this at the moment. And the other topic is seismic, which is coming up now as well, which we haven't really done that much except for the electroseismic. Thank you.